Welcome in Dark Core. Astronomers may have uncovered the first dark matter subhalo in the Milky Way, a massive unseen structure just a few thousand light-years from Earth. If proven real, it could transform our understanding of how the galaxy is built. In this video, we'll explore the discovery itself, the pulsars that revealed it, and what this hidden structure means for the future of cosmology. The study is built on an elegant idea. Pulsars can serve as natural detectors of gravity. Pulsars are neutron stars left behind after supernova explosions, and some of them emit beams of radiation that sweep across Earth with clock-like regularity. In binary systems, where a pulsar orbits another star, the arrival times of these pulses can be predicted with remarkable precision. Any disturbance to the system, even subtle, shows up as a deviation in the expected timing. Dr. Chakrabarty's group examined the timing data of 27 pulsars spread across the Milky Way. They aimed to search for anomalies that couldn't be explained by ordinary astrophysical processes. Out of the full sample, two systems stood out: PSRJ 1640 plus 2224 and PSRJ 1713 plus 0747. Both showed correlated deviations consistent with the gravitational pull of a hidden structure. The team carefully checked for known sources of acceleration. They considered whether gravitational radiation could explain the effect, but the signal didn't match. They also ruled out the Shklovsky effect, which occurs when a pulsar's sideways motion creates an apparent acceleration. Finally, they examined baryonic matter, stars, gas, or dust clouds, but found nothing in the region dense enough to account for the observed gravitational influence. What remained was an unseen mass. Modeling the gravitational pull required something weighing about 24 million suns located roughly 2,300 light-years away. Such an object is invisible at any wavelength and far too massive to be explained by ordinary matter. The only explanation that fits is a dark matter subhalo, a clump of invisible material nested within the Milky Way's larger dark matter halo. This marks the first time a subhalo has been directly inferred from pulsar data in our galaxy, providing a long-predicted but elusive piece of evidence. Why it matters, the importance of this detection lies in how it connects to the broader framework of cosmology. According to the lambda-cold dark matter model, galaxies like the Milky Way are not built from smooth spheres of it. Instead, simulations predict that halos should be clumpy, filled with smaller concentrations which are known as subhalos. These structures act as invisible anchors, shaping how gas collapses into stars and how galaxies grow over billions of years. Until now, evidence for subhalos inside the Milky Way has been indirect. Astronomers have suspected their presence when stellar streams, rivers of stars pulled from clusters, show gaps as if tugged by unseen masses. Others have looked for their effects through gravitational lensing, where light from background galaxies bends due to invisible objects in the foreground. While these approaches provided hints, none gave a clear local detection. That's what makes this result different. By using pulsar timing, scientists bypass the uncertainties of modeling stars or gas and instead measure acceleration directly. Pulsars effectively become test particles in the galaxy, their precise timing revealing gravitational features that would otherwise remain invisible. The discovery also matches what simulations predict about this size. A mass of tens of millions of suns is well within the expected range, large enough to be measurable, but too diffuse in normal matter to light up telescopes. Beyond confirming theory, this finding raises new questions. If this exists, how many others are nearby? Could some be denser, possibly containing primordial black holes or compact objects? And what role do these structures play in shaping the Milky Way's satellite galaxies? A puzzle often referred to as the missing satellites problem. What's next? While the result is exciting, it is still preliminary. The paper has been posted as a preprint and awaits peer review. Independent groups will need to test whether the signal holds up under scrutiny and whether other pulsars show consistent anomalies. The good news is that this is only the beginning. International collaborations like NANOGRA in North America, EPA in Europe, and the International Pulsar Timing Array IPA are steadily expanding their catalogs, timing dozens of pulsars with nanocon precision. As these datasets grow, the chances of detecting additional subhalos will improve dramatically. Each new pulsar added to the network increases sensitivity to small gravitational anomalies across the galaxy. If the technique is confirmed, pulsar timing could become one of the most direct ways to probe dark matter on small scales. Instead of relying on how stars move or light bends, astronomers would have a tool to measure the gravitational influence itself that would allow them to chart a three-dimensional map of dark matter clumps inside the Milky Way. Finding more subhalos would also provide valuable constraints on its nature. Different models, cold, warm, or self-interacting, predict different distributions of clumps. By comparing observations with simulations, cosmologists could test which theory best matches reality. The implications extend beyond astrophysics. Laboratory experiments on Earth are searching for these particles directly while particle accelerators attempt to produce them. Pulsar-based detections complement those efforts by showing how it behaves on cosmic scales. Together, they bring us closer to answering one of the most profound questions in science. What makes up the majority of the universe's matter? Ultra-dark matter may be invisible, but pulsars are giving us a way to trace its hidden structure. If confirmed, this subhalo could be the first step in mapping the Milky Way's dark skeleton. Stay tuned as we uncover more of the universe's invisible secrets. Don't forget to like, share, and subscribe for more space discoveries. Thanks for watching Dark Core.